This talk is about Nimble, a system that provides rollback protection for confidential cloud services. This is joint work with my colleagues at Microsoft Research, as well as our former interns and visiting researchers. The context for this work is also confidential computing. A key building block here is a trusted execution environment, or a TEE. A TEE promises to execute code without an adversary affecting the integrity of the computation or the confidentiality of the data. These adversaries could include cloud insiders, for example, cloud administrators, or external hackers who might gain administrative privileges. The threat model here is that anything running outside a TEE is untrusted and can be potentially malicious. Unfortunately, these TEEs do not have persistent state. Of course, they could use a cloud storage service. For example, they can encrypt and integrity protect their data and then store it in a cloud storage service. Suppose that at some point the TEE updates the data in the cloud storage service. Then later, suppose that an adversary maliciously restarts the TEE. Then the adversary cannot return fake data, but it can return an older version of the data. This is commonly referred to as a rollback attack. Unfortunately, in the current cloud computing offerings, there's no good way to detect such attacks, let alone prevent them. To demonstrate the severity of rollback attacks, consider the secure recovery service proposed by Signal. The goal of this service is to allow users to back up their cryptographic keys under a low entropy pin. Specifically, this service has two APIs. Deposit, which allows a user to supply a label, their cryptographic key, and a pin. And then recover allows a user to supply a label and a pin, and the service returns the associated key if the pin is correct. The key goal of the service is to enforce a per label quota on the number of calls to the recover API with a wrong pin. This is to prevent brute force attacks on the pin itself. To accomplish this, the service runs inside a TEE. It stores a table in the cloud storage service where it keeps track of the number of attempts to recovery with the wrong pin. This data is encrypted under a key that's known only to the TEE. Rollback attacks are a particular concern for this type of service because with rollback attacks, an adversary gets unlimited number of retries. Then for any label, the adversary can call the recover API for all possible values of the pin and then eventually obtain the associated secret key. A key takeaway here is that rollback attacks can be terribly harmful for TEE-based services. A solution to this problem is an append-only ledger service. In particular, it provides three APIs. First, a new ledger takes a label and creates an empty ledger in the system. Append takes a label and a block and appends that to the corresponding ledger. Finally, retail takes a label and returns the last block associated with the ledger. Informally, we need two properties from such a service. First, blocks that were appended cannot be edited by an adversary. Second, the retail API returns the last block that was appended. Now let's see how a ledger service helps detect rollback attacks in the scenario I described earlier. As before, suppose the service updates its state in the cloud storage service. In addition to writing that state, it also writes a digest of that state to the ledger service. Now suppose the TEE is restarted and there is a rollback attack. The cloud storage returns a stale state, but the ledger service will return the latest digest. As a result, certain checks performed by the TEE will fail and a rollback attack is detected. Now let's look at the desired requirements on such a ledger service in the context of confidential computing. I've separated this list into two sets of requirements, basic requirements and additional requirements that must be satisfied for a real-world deployment. As a basic requirement, the service must provide high performance, for example, high throughput and low latency. Second, it should be operated by a single service provider, meaning that it should not depend on anything running outside of the cloud. Third, it should tolerate failures, both machine and network failures. It turns out all of these basic requirements can be met by running a BFT protocol inside TEEs. However, for a real-world deployment, we have three additional requirements. First, the solution must have a small trusted computing base, or a TCB. The second, the solution must support reconfigurations, meaning the service should be able to add new nodes and remove failed nodes without affecting security. Finally, the solution must be easy to understand and implement at large scale. It turns out that many BFT protocols have a small trusted computing base, but they do not support reconfigurations. There are some works that do support reconfigurations, but they don't have a small TCB. In particular, they run complex distributed protocols inside the TCB. Finally, most BFT protocols are notorious for being complex. In contrast, our system Nimble meets all of these three requirements. The rest of this talk is in three parts. First, I'll describe some key insights that underlie Nimble. Second, I'll provide an overview of Nimble's design. Finally, I'll present some experimental results. At a very high level, there are two key insights that enable Nimble to meet all the three additional requirements. First, it separates safety and liveness concerns in BFT protocols. Second, it leverages replication protocols implemented inside existing cloud storage services. I'll unpack each of these insights in turn. Recall that BFT protocols provide safety and liveness with a unified protocol. In our context, safety means that retail API returns the latest block that was appended to the corresponding ledger. And liveness means that all submitted requests are eventually processed by the service. However, in the setting of confidential computing, a service provider can trivially violate liveness, for example, by just denying service. So as a result, Nimble needs to guarantee liveness only when the provider is honest. So our first insight is to separate safety and liveness concerns. In particular, Nimble runs a small safety critical code inside the TE. This directly leads to a small TCB. Nimble then runs code that concerns with liveness outside the TCB. Our second insight stems from the fact that cloud storage services internally implement complex replication protocols. So Nimble's second insight is to leverage existing cloud storage services for the purpose of liveness. In particular, this obviates the need to implement a complex protocol as part of Nimble's implementation. In fact, this substantially simplifies the overall system. In the next part of this talk, I'll provide an overview of Nimble's design, starting with its architecture. At a very high level, Nimble is architected like a traditional cloud service. It contains one or more coordinated processes that receive requests from the client, and then they provide responses. It internally uses a cloud storage service where these ledgers are stored as cryptographic hash chains. This, of course, does not provide any rollback protection. So we use a set of endorsers, which run a small amount of trusted code inside trusted execution environments. There are two reasons why this architecture achieves high performance. First, operations on different ledgers can proceed in parallel. Second, the coordinator performs a few storage operations and a single round trip with the endorsers for each request. This is also simple because it uses a replication protocol implemented inside the cloud storage service as a black box. This architecture also achieves a small TCB because of how an endorser works. At a high level, this endorser runs inside a TE, and it has its own secret key, which it uses to sign responses. Inside its memory, it maintains a table where there's an entry for each label, and for each label, it stores the associated tail of the hash chain. The code that runs inside this endorser is also small. It exposes two simple APIs, one that allows us to append an entry to the tail of the hash chain, and another that returns the current tail of the hash chain. In the absence of reconfigurations, this is roughly all of the code that runs inside a TE. As a result, Nimble achieves a small TCB. Now let's see how Nimble achieves fault tolerance. First, cloud storage is already fault tolerant, so we don't need to do anything. Second, the coordinator is stateless. So if a coordinator crashes, we can just restart another one, and in fact, we can run many coordinated processes from the start. Finally, for endorsers, we use a set of endorsers where a minority can crash at once. So this raises a question: what happens if an endorser crashes and loses all of its memory? And of course, a real service must always maintain a sufficient level of fault tolerance. To address this, Nimble allows adding new endorsers and removing failed ones. One challenge here is that it should not be possible to misuse this ability to roll back the state of the system. In a nutshell, Nimble's solution works as follows. An untrusted coordinator initializes a new set of endorsers, which I've denoted here with N. It then calls an API called finalize on the existing set of endorsers. The existing endorsers finalize their state and provide a signed report on their state. Once an endorser is finalized, it erases its private key and does not process any further requests. The coordinator waits for a majority of existing endorsers to finalize their state. The coordinator then calls a new API called activate on the new set of endorsers. These endorsers perform a set of checks, and only if those checks pass do they start processing requests. Note that a malicious coordinator cannot activate another set of endorsers because the signed reports are meant for a particular set of endorsers. In fact, a key invariant here is that a coordinator can activate a new and unique majority of endorsers with some state S only if it finalizes an existing majority whose collective state is S. The upshot here is that the TCB remains small even after adding support for these reconfigurations. In the next part of this talk, I'll provide some experimental results, starting with our implementation. We have built a prototype of Nimble in Rust and C++, where endorsers can be deployed in different TE platforms, for example, Intel SGX, AMD SNP-SEV, SNP, and so on. This prototype supports endorser reconfigurations. It can also use different storage services for storing hash chains. We have also integrated Nimble with HDFS to add rollback protection to HDFS. We have open sourced all of this code on GitHub. We have also evaluated Nimble's prototype. In this talk, I'll focus on answering two key questions, and the paper has additional results. First, I'll show how Nimble's TCB compares with alternative solutions. Second, I'll depict the latency and throughput of Nimble. Here is a table that depicts the TCB size of Nimble and compares it with prior work. It also shows whether the depicted system supports reconfigurations or not. One caveat here is that these numbers should be treated as ballpark numbers because these different systems are implemented in different programming languages and coding styles. However, one key takeaway here is that Nimble's ability to support reconfigurations does not bloat its TCB. In particular, the TCB size is comparable to solutions that don't support reconfigurations and much smaller than the ones that do support reconfigurations. Here is a slide that depicts Nimble's throughput and latency with different underlying storage services. I want to highlight two takeaways here. First, the read performance is unaffected by the choice of the storage service. This is because reads are serviced directly from the endorser's memory. Second, for appends, Nimble inherits the performance of the underlying cloud storage service used. Finally, to summarize Nimble, it addresses a key security problem in the context of confidential computing, namely the rollback attacks. Nimble is a cloud service with a unique combination of properties, namely a small TCB, high performance, and fault tolerance with support for reconfigurations. And our implementation of Nimble is available as an open source project. With that, I conclude my talk. Thank you.